From sending messages across the universe in an instant to breaking the speed of light barrier. Have you ever wondered if faster than light communication could really become a reality? But what could it mean for our future? The speed of light is a constant rate at which light travels. It is approximately 299,792 kilometers per second, or about 186,282 miles per second, which is the fastest speed at which energy, information, or matter can propagate through the vacuum of space. This constant, often denoted as c in physics, forms the foundation of Einstein's theory of relativity with enormous consequences for our understanding of the cosmos. Historically, the first quantitative measure of light speed was accomplished in 1676 by the Danish astronomer Ole Christensen Romer. Through observations of Jupiter's innermost moon Io, Romer noticed that the moon's orbital period varied depending on Earth's distance from Jupiter. As Earth approached Jupiter, the light from Io had a shorter distance to travel, resulting in an increase in the moon's orbital velocity. Conversely, when Earth moved away, the distance increased, leading to a longer period. By analyzing these variations, Romer estimated the speed of light to be approximately 220,000 kilometers per second. This groundbreaking discovery marked a significant advancement in understanding the nature of light, providing crucial evidence that light has a finite speed. According to the theory of relativity, an object's mass increases exponentially as it gets closer to the speed of light, indicating it needs infinite energy to travel at or above this speed. This led to the general consensus that faster-than-light travel and communication are impossible under our current understanding of physics. However, theoretical physicists have offered several exceptions and loopholes. For instance, tachyons are hypothetical particles that move faster than light. If they exist, they might change our communication approaches. One of the most innovative concepts of FTL communications is based on the theory of quantum physics. Quantum entanglement occurs when two or more particles interact in such a way that the quantum state of one particle cannot be determined independently of the state of both particles, even if the particles are separated by a vast distance. Albert Einstein famously defined the phenomena as spooky action at a distance. Concerns about the potential for FTL communications are raised by the fact that this seems to be happening faster than light. Moreover, quantum communication transmits information based on quantum entanglement principles. Quantum key distribution, QKD, is a popular strategy that employs particles that are bound to generate a common, secret cryptographic key between two particles. The key may be used to encrypt and decode interactions, resulting in secure communication. In a basic QKD setup, two particles, often referred to as Alice and Bob, share pairs of entangled particles. When Alice measures her particle, the result instantaneously influences Bob's particle, allowing them to generate a matching key. An attempt by an eavesdropper, also known as Eve, to capture the particles would disturb the entanglement, thus alerting Alice and Bob to the invasion and ensuring the security of their communication. Significant progress has been made in the field of quantum communication. Some notable advancements of this are quantum experiments at space scale, QUESS. Launched by the Chinese Academy of Sciences, the QUESS satellite is also known as Moniscus, which successfully showed quantum entanglement and QKD over distances exceeding 1,200 kilometers. Quantum networks over metropolitan and intercity distances are now possible because of developments in fiber optic technology. China and the Netherlands have created urban quantum networks that show how they can be used in actual circumstances to provide secure communication. This marked a significant milestone in proving the feasibility of satellite-based quantum communication. Another theoretical possibility involves using wormholes or warp drives. Wormholes, often referred to as Einstein-Rosen bridges, are theoretical passages through space-time that could create shortcuts for journeys across the universe. The concept arises from solutions to Einstein's field equations and general relativity. These equations demonstrate how mass and energy alter space-time, creating the phenomena we know as gravity. It can be visualized as a tunnel with two ends at separate points in space-time. It could theoretically connect vast distances, allowing for instantaneous travel between the 2 points. This would not enable just communication, but also potentially FTL travel. However, establishing and maintaining stable wormholes offers significant challenges. According to theoretical concepts, a wormhole would require massive amounts of negative energy or exotic matter to remain open. This exotic substance is theoretical and has never been detected in nature. Warp drives are another popular concept, proposing a method of FTL travel by bending or warping space-time around a vessel. The most famous theoretical models for warp drive is the Alcubierre drive, proposed by physicist Miguel Alcubierre in 1994. Space-time is compressed in front of the vessel and expanded in the back by the Alcubierre drive, which essentially creates a warp bubble. Within this bubble, the vessel would stay still while space-time shifted around it. This would overcome the gravitational restrictions and enable the spacecraft to travel faster than light without locally exceeding the speed barrier. There are substantial technological challenges. The extremely high control over particle states necessary for quantum communication is beyond the capabilities of current technology, which is still in the early stages of development. Wormholes and warp drives would need significantly more energy and materials than we currently have if they were possible. There are also physical limitations. Relativity states that anything with mass can't even go closer to the speed of light. Even in quantum physics, the no-signaling theorem implies that entanglement cannot be utilized to convey information faster than light. While embedded particles impact each other in an instant, this effect cannot be controlled or utilized to deliver specific messages, keeping the light speed limit for information transfer. A major change in our comprehension of physics would be necessary to overcome this. Beyond the technical and physical challenges, FTL communication raises several ethical and philosophical issues. The ability to communicate instantly across long distances might have significant implications for privacy and security. For example, if an entity could transmit and receive information throughout the cosmos instantly, it may evade traditional communication networks, possibly compromising data safety and information protection. Despite challenges, research is ongoing. Scientists are making progress in quantum communication as demonstrated by studies showing entanglement over ever greater distances. Another important field of research is quantum teleportation, which transfers the state of a quantum particle from one location to another in an instant. This method does not move mass or energy faster than light, but rather instantaneously transfers information about the quantum state, which might be critical in the development of quantum communication networks. Advances in quantum field theory provide innovative methods to generate and manipulate negative energy, though on a very tiny scale. The Casimir effect, which includes negative energy concentrations in the setting of quantum field theory, is being researched for potential applications. Recent theoretical research focused on the possibility of generating traversable wormholes. These conceptions, however, remain hypothetical since they are based on untested assumptions about the nature of space-time and exotic matter. As we wrap up, we've explored the possibilities of communication faster than light, including the limitations provided by the state of physics as we now understand it, and the theoretical potential that may one day make it possible. So, what are the most significant scientific challenges that need to be addressed to make faster than light communication? Share your thoughts in the comments and don't forget to like and subscribe.